So we're going to look at a particular example of assessing fertility risk with R via a code example, and here we will see in particular how we use logistic regression, which is a form of linear regression. Binary logistic regression is a regression model used where the predicted outcome is a binary. It's like an on-off type of variable. This kind of model can only be tested in the aggregate, even though it makes individual level assessments because of the probabilistic nature of its predictions. So for particular set of inputs, you might predict a 30% chance of your outcome. If the outcome happens or doesn't happen, for that particular individual, you can't say the model is right or wrong. What you need to do is you look at how it behaves for many individuals, and if the probabilities approximately match, you've got a good model. The intuition for binary logistic regression is that your coefficients that you're going to get from your analysis can help indicate whether a predictor makes an outcome more or less likely. So for each input that you put in and you want to see how it affects the output, if it has a positive or a negative coefficient, that tells you, does it make my outcome more or less likely? So we're going to look at a fertility data set code example. It's in the prediction folder. It's fertility.logit.r. In this data set, we're going to look at a number of factors that can affect whether individual males are more likely to produce normal or abnormal sperm. We'll see which factors make abnormal sperm more or less likely. Okay, so we are working off a data set that is in the prediction folder. Once again, I'm going to require a data table as a very handy way of selecting data and filtering data. So we're going to read in our data set, and let's take a look at what we have now. We have age. We have the outcome, which in this case, an outcome of 1 is an abnormal shape of sperm. We have whether the individual is sedentary, whether they smoke, and whether they have experienced some form of traumatic accident. So when you are doing prediction, right, when you are doing things where you move into having a right and a wrong answer, you usually want to have a training set and a testing set. And what that means is that to create your model, you do have to sacrifice some of your data, your testing data, set it aside and not use it. And the reason for that is you want a way to validate your model once you have completed it. So if you train on data, you can't test on that data, right? That data has created your model. So it would be a logical fallacy to turn around and say, well, the data I trained on is so good because look at the results it gives, right? You need to have independent ways of assessing your model. So one way you could do this is you can say, well, how many rows do I have? We'll do n row on df. We have 10,000 rows. So one thing you could say is, well, I guess I'll take about 80% of that data and I'll train my model. And I'll use the rest to test. So you could do something like this. In general, don't do this. This is not even just a healthcare concern. In general, there could be reasons that your data and the order it has come in is non-random. And that's certainly true in healthcare data, right? Data could be grouped by hospital or by neighborhood or by gender or by age. You don't want data sorted that way because that would mean that the data you're training with is fundamentally different from the data you're testing with. So you want to take a random subset. In this case, we'll take a sample size of 80% of our sample, and we will separately get our training indices and our testing indices, and that's the way you always want to do it. We set aside our testing indices for later, and we get our training data for now, so we will subset our data frame to take both of those. And actually in R, which is written for statistical purposes, it's extremely easy to do a binomial logistic regression. It is part of the base package of R. It's a function called GLM, which is short for generalized linear models. A binary logistic regression is a generalized linear model. We are going to regress outcome on everything else. So you notice here I'm not doing exploratory data analysis first. In a real world situation, I probably would want to, but here I'm going to take the lazy way out. I'm going to regress on everything, use a link function of a logit using my training data. So we're going to run this logistic regression on 8,000 individuals. Boom, notice how amazingly fast it is. That's another feature of linear models. They are generally very computationally efficient, even for large data samples. And if you are new to R, you will see that what's very handy about R is for most objects, you can run a summary. And if we run a summary, what I will call your attention to right now is first, it gives you your formula back. So you can run many models and compare them, and the model will hold on to its parameters needed to compare. And then if we look here, what we see, we ran on everything. So it has turned out that age does not seem to predict the misshapen sperm, but sedentary activity, smoking, and trauma do. And the other thing we will notice is that sedentary behavior and smoking both have a positive value, whereas trauma has a negative value. So interestingly, it seems as though being sedentary and smoking lead to misshapen sperm, which is not so surprising. But trauma seems to do the opposite and somehow make it less likely. And then what gets a little complicated in medical and healthcare situations is, of course, humans are thinking animals. So you could say, well, that means that somehow trauma fixes your reproductive apparatus, but I would say more likely is there's probably some behavior associated with that, right? So for example, I would wonder if we actually have correlated variables and possibly trauma leads to someone being less sedentary. So you have to worry that maybe your variables are correlated. Or I would say there's some other behavioral or psychological reason that trauma has somehow corrected this tendency that people might have to have misshapen sperm. If we want to check the fit, right, so there'd be a bunch you'd really want to do here to make sure this makes sense and also make sure that your original data meets the requirements of a binary logistic regression. But for now, we can check the fit just by testing, right? So we are going to put our fitted results via a prediction of the test data into a vector, right? So we put our fitted results in. And remember, from a logistic regression, you actually get like a risk prediction. You get a probability of something happening. You, at the end of the day, then have to assign that to a 0 or 1 yourself. So we're going to use a cutoff of 0.5. We're going to say, if the result is greater than 0.5, so if your chance of having misshapen sperm is more than 50%, we're going to give you a 1 and say you do have misshapen sperm versus a 0. So we're changing the model, which actually predicts a risk, into a binary outcome. We can do that with this line of code with the if-else function. And then we can assign that back to the test just so that we can keep track of what our model has assigned. And finally, we can use the table to see how our predictions and our outcomes match. So in this case, I can see that when someone has a 0 outcome, 973 times I have predicted a 0 outcome and 248 I have not. And on the other hand, when someone has a 1, I have predicted a 0 475 times and I have predicted a 1 304 times. So one thing you should spot here that you would investigate at further length is the fact that I seem more likely to predict a 0 than a 1, even in the case of people who actually do have an outcome of misshapen sperm. So this would only be a first pass at a linear model. When you were doing this in a real situation, you would, of course, first make sure that your inputs matched the assumptions of the binary logistic model. And then once you got to this outcome, you would start wondering why your accuracy was so low. And that's when you could begin investigating how your coefficients are related to one another, or alternately, whether there's something about the baseline probability that just makes your model always rewarded for predicting a 0. But what you notice is that just from this, what we can do is ask some people a few simple questions about their lifestyle and their life history, and at least give them a rough probability assessment of something affecting their fertility, whereas otherwise they would have no information. So even a very crude implementation of a linear model can be tremendously helpful.